We will begin our talk. I am here and lucky to introduce Amrita. She's going to be giving a talk on building trust in AI.
Perfect. All right. Good morning, everyone. Very excited to be here. Very exciting talk, the last one. Okay, let me see. Can you hear me in the back? Yeah? Okay, perfect. All right. Hi, I'm Amrita. I'm a final year PhD candidate at ASU, and I'm also an incoming applied scientist at Amazon. And in this talk, I'll be giving a presentation on building trust in AI, on safe and responsible use of LLMs. So I come from more of a deep learning and natural language processing background, so it might be interesting to sort of see how we do things in that side, right? All right, so we know that large language models, yeah. Yes, absolutely. Mm-hmm. And they're up on my website already right now, if you want to follow along. Yeah. Okay. So we know that large language models have sort of emerged to be these pervasive, the most pervasive among generative AI technologies. And we have so many of these chat assistant type models coming out pretty much every other day, right? And most of these models are, very easily accessible via APIs. You also have a lot of these open source or open weight alternatives as well that are available on platforms like Hugging Face, and many of these wrapper sort of software like Olama, as the previous speaker was talking about. And many of these models are small enough that you can even run these on your standard consumer GPUs. There's a lot of community support as well when it comes to the different packages and libraries that make use and development of these models very easy. So, of course, the barrier to entry is pretty low right now, which is very exciting. And we are seeing a lot of really nice applications and use cases of these language models right now. So they're, of course, general purpose task solvers, and we have seen very good evidence of these models being really good at a variety of different tasks. And more recently, we've also seen sort of more useful and reliable applications when used in agentic settings. But, given the ease of access of these models and how accessible these are, we see a higher potential for misuse of these models as well when it falls into the wrong hands. So I'm going to talk about some sort of motivating examples of misuse of these models. And I think the biggest threat that we see being talked about, especially, is LLM-generated misinformation or disinformation, especially given the scale at which it can be generated by malicious actors. So large language models can be very easily instructed using natural language instructions to generate disinformation. And you can make these models generate disinformation following certain narratives or claims, which are false. And there are a lot of studies that have sort of investigated how easy it is to generate such misinformation, from different domains, intents, and having different types of errors and factual claims. We've also seen some examples of AI-generated fake social media profiles. And recently, I've been seeing these a lot on places like LinkedIn or Facebook. And, for people like us, people in this room, it might be easier for us to understand which profile is AI generated or fake, and there's a bot that's, controlling that profile. But think about how difficult it might be for the lay person to understand, and they might, exchange information with these accounts. So this is also an emerging threat that we are seeing recently. And sort of following along on that, we've also seen examples of LLM-generated social engineering attacks. And we actually did a study recently where we generated sort of social engineering attacks, in a multi-turn conversation with LLMs. And we investigated these 4 different scenarios. So academic collaboration, recruitment, academic funding, and journalism. And we saw that in majority of the cases, the victim actually got convinced enough to give out their personal information. So this just goes on to say that, it's so easy to misuse these language models to generate these malicious attacks. But of course, we all know that, it's not like LLMs are all bad, right? They're super useful, and it's sort of up to us to figure out how to use these models to the best of their abilities. So that's sort of the philosophy behind this talk. And I want to acknowledge this dual role of large language models. So on one side, as I mentioned, LLMs can generate malicious content or can be misused to generate malicious content or disinformation. These models also have intrinsic issues and vulnerabilities, and they can, be jailbroken or attacked and can therefore elicit harmful content and malicious code. But on the brighter side, we have also seen these models being great at, in general, text generation, code generation. I'm sure a lot of us use code assistants on a daily basis. And recently, we've also seen a lot of very interesting math or reasoning applications as well. Some more extended applications that we've seen in the deep learning and sort of data mining community is the use of LLMs for augmenting data or generating synthetic data. All right, so that sort of motivates this talk. How do we get the best out of LLMs, right? So how can we build frameworks that enable safe and responsible use of LLMs? And we sort of want to do this with 2 focus areas in mind. We want to build frameworks that can detect and mitigate LLM threats post hoc. And we also want to build frameworks that can systematically leverage these LLM capabilities while understanding what they are bad at. So the rest of the talk is going to be divided in sort of these 3 directions. First, I'm going to talk about some detection methods. And why is this important? I'm going to explain the importance of AI-generated text detection or LLM-generated text detection. The second one is going to be on mitigation. So how can we reduce the harmfulness of LLM outputs? How can we mitigate that? And finally, I'm going to briefly talk about an example of a systematic use case of LLMs in a very interesting application. So how can we use LLMs to do something as difficult as model explainability? All right, so let's get started with the first part, which is detection. So we know that AI-generated text detection is not a new problem. It has only been exacerbated in the recent years because of so many LLMs that are out there and that are so easy to access. And then we can also have unintended harms that are caused by AI text. So not all AI text is malicious, right? Or is created with malicious intent. So some of the areas where AI text can have a detrimental effect. The first one, as I gave you an example already, disinformation and manipulative content. We've also seen different types of phishing emails and other cybersecurity threats. In education, AI-generated text can have, cause plagiarism or violation of academic integrity. And finally, we can also have infringement of copyright or intellectual property rights. So, and given the scale at which these LLMs are being used to generate text every day, we need sort of automated methods for detecting what is AI and what is human, or at least giving us some kind of signal as to what is AI and what is human written. So there are some different methods that are out there for detecting AI or LLM generated text. And the whole idea behind these automated methods is that there is some statistically significant difference that exists between the human written texts and the AI generated text. And, intuitively you can think of it as a human, I'm not sampling from a distribution when I'm speaking, right? I'm not sampling the next word from a distribution. But that's how these LLMs work, and therefore there are some statistical artifacts that are sort of left behind in the generation that a model can pick up. It might be imperceptible to humans, but not to statistical methods. So here we have three broad classes of methods. The first one is heuristic-based methods. So you sort of look at some kind of heuristic in the text, and these are typically zero-shot methods. So these could be things like log probabilities or likelihoods, perplexity scores, things like that. The second one, this got famous in the last couple of years, is essentially watermark-based methods. And this responsibility sort of lies on the model developer side. The model developer has to sort of include these watermarks in the LLM development. That can then be later picked up by some detection method. And finally, we have these model-based or fine-tuned detectors. So these are essentially some deep learning-based models that are then trained on some kind of data set. So these data sets are labeled data sets that have human written text and some kind of LLM generated text. And essentially you frame it as a classification problem. So these are some examples of one work from each of these families. So a very famous heuristic-based method was this method DetectGPT that came out in 2023. And essentially what they do is they have some assumptions on the log probabilities of the text under that specific model. So they are assuming some kind of like a white box access to the model, and they assume this curvature on the log probabilities of the human written text versus the AI generated. So there is some kind of difference between these two behaviors. And then for the watermark-based methods, this is actually the image from the first paper that got really, really famous in the context of large language models. Even the watermarks existed even before this. So essentially what happens here is when you're the LLM developer, you essentially want to include this functionality in the LLM that during generation, the model is forbidden to sample from sort of like a red list of words. But of course, as a human text does not have this constraint, so you sort of have this artificial statistical artifact that you can then detect. But again, one thing I want to add when it comes to the watermark-based methods is, the onus lies on the model developer. So it can be well implemented when it comes to sort of the proprietary models. But because we have so many of these open source models out there that, again, undergo a lot of fine-tuning and model merging and things like that, it's very difficult to implement watermarks at that scale. All right. So finally, we have these model-based methods, the third one, and these are, as I mentioned, these are detectors. So these can be, built using some pre-trained language models like Roberta back in the day. These are fine-tuned with labeled training data, and these, of course, do post-hoc detection. So overall, we've seen the best performance coming out of these model-based methods. So let's focus on that. Okay. So the problem of these model-based methods is that, you sort of have your label set fixed, human and some specific LLM generator. But how do we deal with these new generators or language models that are coming out? A very naive solution to this would be to create new data sets for every new generator that comes out and retrain your detector. But of course, this is infeasible in practice and it does not scale, right? So a potential solution here could be that, you have access to all this unlabeled text that, humans are creating. We're using these language models every day. So we have a bunch of unlabeled data from these new language models. And I'm using the word generators and language models interchangeably here. And we also have the labeled data from the older generators or the older language models. So we can sort of, try to learn domain invariant features across these different generators. So the whole problem here that we are trying to solve is the generalization problem. Can we generalize the detection performance to the new language models? So we come up with this very interesting framework For this, I'm not going to go into the details of this framework, but essentially, we try to learn the domain invariant features across the source and target generators so that we can sort of perform unsupervised detection of text from the new language model that we do not have any labels for. So for our experiments, we have a data set of news-style articles, and we also generated our own ChatGPT, or at the time it was GPT 3.5, generated data. And we have a bunch of different baselines that we compare with. And the different language models that we test out on sort of have different architectures. So I'll quickly go over the results. So a source-only baseline is where you train this framework only on the source domain, so the source generator, and you test it without fine-tuning on the target generator. So this should serve kind of like a lower bound. The supervised one is basically a model with the same backbone, but it's trained with target labels in a supervised way. So this is supposed to be an upper bound, and these two blue bars correspond to this method that I just talked about. And we see that our method performs pretty well, and it performs better than these source-only models. And this is some comparison with the unsupervised baselines, as I mentioned. And again, these are, in this table, these are the AU ROC scores. And we see that this framework performs much better. And we also wanted to do a little case study on GPT 3.5 generated news, as I mentioned. So the whole idea is that if you train on data that comes from much smaller generators, can you still generalize to text that is coming from much larger models like GPT 3.5? And we saw that we can do it to a certain extent pretty well. But these numbers might be a little bit inflated because, you know, news articles have some inherent structure that might make it a little bit easier to detect. All right. So, so this concludes that first work that I wanted to talk about. And this is interesting. The results are promising, but I do want to mention that there are lots of interesting things that can be done on top of this. So we haven't really tested out adversarial test cases. So what happens if you have a news article or a piece of text that is generated by an LLM, but then you do some human edits on it? Is it still detectable? So there are lots of interesting sort of experiments that can be done on top of this. All right, so moving on to the second part. Mitigation, how can we perform sort of steering, and I'm going to explain what that is, for enabling safe LLM outputs. All right. Okay, so the way LLM safety is enforced or implemented nowadays is mostly through post-training and alignment. And, you know, there can be some red teaming steps in between somewhere in the pipeline. So usually back in the day, what used to happen is you have this base model that is then fine-tuned using human instructions. So that's your SFT step. And then you have your alignment step, which uses RLHF or reinforcement learning with human feedback using a reward model. And this reward model is trained using a lot of human preference data. More recently, we have started seeing a lot of use of synthetic data and different types of optimization methods, newer optimization methods, which are more sort of data efficient. And we also see more continual alignment type methods. So that's very exciting. But overall, alignment is very resource intensive. And, you know, safety standards and policies can keep changing. So how do you adapt to these new policies, right? And the second point is also very interesting. These models that you have out there, especially the open source ones, it's great that they're open source, but then people use these models to fine tune on their respective downstream tasks, right? That's the whole point of having these open source models. But it has been shown that once you fine-tune these models, you can lose the alignment of these models. So you lose the safety training and everything that you did in that previous step using all that data. The other issue here is that we might need adaptable policies for safety training. So essentially, a model that works really well for a US context might not, or might be even considered offensive in a Middle Eastern context. So policies should be customizable or adaptable. And maybe a potential solution could be that you move some of this post-training or alignment more to the inference side, and you perform some kind of inference steering of these LLM outputs. So there are some inference time or model editing kind of approaches that have been explored. The first sort of family of approaches that I'm going to talk about does this in the decoding step. So essentially, you have a language model and you give it a prompt and you wait for it to generate the output. And during the generation, during that decoding step, there can be a safety evaluator model that evaluates the current generation, and if it passes these different policies and safety criteria, then it's fine. Otherwise, you go back and regenerate. So this is great in theory, but of course the issue here is the high latency. You cannot really have this model deployed for general use. So another family of methods that sort of fix this problem is by doing some kind of model editing or engineering on the weights or the activations of the model. So this concept of activation engineering has been used for, including or injecting certain concepts in the generated output. So the way this works is you maybe extract activations that sort of correspond to a specific concept. You compute some kind of a steering vector, and you use that steering vector during inference time to steer the model outputs. But up until recently, we didn't really see much use of this method in safety. So we were really interested in seeing whether this would even work. Because it works really well in injecting other kinds of concepts. So that brings me to the next piece of work that I'm going to talk about is inference time steering, but for sort of specific to harm categories. So we wanted to look at different categories of harm. So these could be adult content, hate speech, self-harm, these different kinds of concepts. And we wanted to have more fine-grained control on the steering. So this is what our overall sort of framework looks like. You have white box access to an LLM, and you have some data sets that correspond to safe and unsafe text or text prompts. And you essentially get the activations of the LLM when you feed in these prompts to the model. And you have a set of harmful activations, and you have a set of harmless activations. And you can compute some kind of steering vector. So the steering vector is supposed to sort of correspond to the concept of safety. And like intuitively, you can think of it as if you add this steering vector during generation, your outputs are going to be steered more towards regions of safety in the vector space. So this is the framework in a little more detail. So first, as I mentioned, we record the activations from the forward pass for the harmful and harmless data sets. And then we compute the steering vector. So we have two methods of computing the steering vector. These could be the guided steering vectors or the unsupervised steering vectors. The guided steering vectors use an external safety classifier. So essentially, the idea here is that many of these models are already fine-tuned or aligned for safety, and these models can often respond or refuse to respond to unsafe prompts. So we want to reinforce that behavior while sort of negatively reinforcing the harmful behavior. So what we do is we feed in the unsafe prompts, and we extract the unsafe activations only after verifying that it actually results in a harmful LLM generation. And we do this verification by using an external safety classifier. But for the unsupervised ones, we just assume that, the representation of the unsafe prompts is unsafe and the representations of safe prompts is safe. And we just compute the steering vector as a sort of like a difference in means between these activations. All right. So in step 2, what we want to do is we have this steering vector that we computed from the previous step, right? And this vector corresponds to this concept of safety. So we want to add it to one of the intermediate layers with some positive multiplier, like a scalar multiplier. And as I mentioned, we want to enable sort of fine-grained control. So we compute one vector per harm category. And we add this computed vector into one of these intermediate layers, as you can see in this diagram over here. So in our experiments, we mostly deal with the Llama architecture, and we have 32 layers, and we see that, if you do this sort of steering in the middle layer, which is layer 14, when it's indexed from 0, it's the most effective in most cases. And the earlier layers usually do not have much effect when it comes to the safety steering, and same goes for the last few layers. And also another interesting thing that we noticed is if you try to steer the attention weights, you get the best sort of result when it comes to safety. And the other kind of weights don't really have that much of an effect. So MLP layers or sort of residual weights. All right, so I'm going to quickly go over the data sets and the experiments we did. So these are the two data sets we used. Both of these have harmful questions or harmful prompts from a variety of categories. And because you also need a safe counterpart for the data, we generated some of our own data for the first data set. Otherwise, there was already a safe category in the second one. And for the metrics, what we want to see in the results is we want to see a drop in the percentage of unsafe responses after steering. So we first measure the percentage of unsafe responses for the naive generation, that is without any steering, off-the-shelf LLM. And then we perform the steering, and then we measure the percentage unsafe responses. We also want to look at the text quality using the helpfulness and coherence scores that we get from a reward model, an off-the-shelf reward model. All right. So here we want to see whether this category-specific steering actually helps to reduce the harmfulness while retaining text quality. And I won't go too deep into the detail, but I'm just going to explain the main sort of observations that we see. We test on these two models, Llama 2 7B and Llama 3 8B. And here I have results for 3 different categories. You can see the intervention layer that worked the best. So somehow for everything except adult content for Llama 2, we got the best performance when we intervened in the middle layer, which was 14. And here, these numbers are essentially the drop in the unsafe responses, the percentage unsafe responses from the naive generation to the steered generation. And these are the helpfulness and coherence scores. So essentially, we want the percentage unsafe responses to be as low as possible. We want the drop to be high. And we want the helpfulness and the coherence scores to be retained as much as possible. So we see that, for Llama 3 8B, we get really good performance when it comes to the unsafe responses or the drop in percentage unsafe responses. The coherence scores are retained, but the helpfulness does take a hit. So there can be some better ways of optimizing this trade-off. All right. So the next, in the next research question, we sort of wanted to see whether the additional guidance that we used in the guided setting of generating the steering vectors actually helped in improving the steering performance. And we see that it does help in sort of retaining the helpfulness or even increasing the helpfulness, as you can see from these numbers. So the helpfulness in the naive generation was much lower, but for the steered generation, we get a huge bump over here. while also reducing the percentage unsafe responses. So using that external guidance definitely does help. I have a lot more results in the paper that is linked in the slides. So, you can go to my website and look at these slides and the paper list. And I'm going to skip over those in this presentation. So it's very exciting. We did this sort of inference time steering for safety. I think we were the first ones to do this for safety. We didn't know if it would work, but very exciting that it did. And it sort of opens up the possibility to do a lot more in this area. And the first one is optimizing the trade-off between the percentage unsafe responses and the quality. So in our work, we didn't really control for the quality. But you can probably get better results if you have some kind of optimization over there. You can have sophisticated methods of pruning out the activations or important sampling of activations for computing the steering vectors. That can be very interesting. And I motivated with this last point, but we didn't actually implement it. But it would be very interesting to sort of incorporate custom policies into these steering vectors. So can we, have steering vectors that encode certain custom policies, maybe specific to a sociocultural context? All right. So finally, let's go to this last example of a systematic use case. And I'm going to talk about LLM-guided model explainability. So I'll give you a brief background on what I mean by model explainability, coming from a deep learning or NLP background. So essentially, we know that most of these NLP models, and especially text classification models, are black box in nature. So you feed in some input text, you get a label, and that's it. You don't know why you got that label. And this is because most of these state-of-the-art models use pre-trained language models as the backbone. And these are either transformer-based architectures or some kind of complex multi-layer deep learning architectures. So these are, of course, not interpretable by design. And also, these are very difficult to explain post hoc. And this is important in more real-world applications where you need to give the user some understanding of why your model predicted a specific label. So even if it's not, a faithful label, the user has to have some understanding just for the user satisfaction side. So one way of doing this is by using counterfactual examples and counterfactual explanations. And I'll quickly explain what that is. So a counterfactual explanation essentially asks kind of like a causal question, that what could have changed the decision of the classifier. So something like, if event A1 did not occur, then the label would have changed from Y1 to Y2. So you're trying to sort of understand what feature in the input led to the label, or what can you change in the input that would flip the label of the classifier. So this is an example on the right. This is a natural language task. It's a very simple example of, say, a sentiment classification on a movie review. The first one says this movie was horrible on every aspect, which is labeled negative. And if you just change this word to fantastic, the label is positive. So this example here is a counterfactual explanation because it shows you what changed in the input that changed the label of the classifier. So these explanations are great because these are, simple, human understandable, and it captures the actual model behavior. And this is also black box in nature. You don't even need access to the model. You just need access to the input and the model predicted label. And although this is debated, but it may provide some insights on what causal features the model has actually learned. So this is a very interesting task, and we kind of wanted to see whether LLMs can be used for this kind of a task of causal explainability. So this is the framework we come up with. This is a pipeline where we use LLMs with a bunch of different prompts, some very sophisticated prompting techniques. And over here, this is a prompt that we use to sort of prime the model, that you are an Oracle explanation module in a machine learning pipeline. And then we follow 3 steps, following sort of the standard causal graph way of solving problems or getting labels for a specific input. So in the first step, we use the input text and the model predicted label, and we add this kind of a prompt. This is a much shortened version of the prompt to just give you an idea of what this step does. The longer prompts are in the actual publication. So the first step is, in the first step, we try to extract the latent features that resulted in the prediction. So latent features usually mean something unobserved, and I'll show you an example of that. So in the second step, we prompt the model to identify the words or the input features that were associated with the latent features. And finally, we ask the model to use or edit a minimal set of these identified words to flip the label, essentially generating a counterfactual explanation. So I'll explain this with a small example. So this is a natural language inference task. It's a very standard task in NLP. And basically, the task is you have 2 sentences. The first sentence is called a premise, and the second is called a hypothesis. And you have 3 possible labels: contradiction, entailment, and neutral. So the label will be contradiction if the hypothesis contradicts the premise. The label will be entailment if the hypothesis entails the premise, so on and so forth. All right, so in this example, the premise is a woman with a green headscarf, blue shirt, and a very big grin. Hypothesis is the woman has been shot. And of course, the label here is contradiction. And step 1, using our pipeline, we extract the latent features. So these are the very interesting latent features that our pipeline extracted. So inconsistency in text, contradiction in events, negative sentiment, all of these. So, these are quite high quality, and as a human, I don't think I would have been able to come up with this kind of a set of really high quality features. Then in step 2, we identify the latent features that are associated with these input features that are associated with these latent features, and we get a set of words and phrases. And finally, in step 3, using our pipeline, we minimally edit the input to generate this counterfactual. So as you can see here, the premise is exactly the same, but in the second sentence, only 1 word has been changed. The woman has been photographed. And the label here is entailment. So this is a successful counterfactual explanation. So the whole objective here is to give the user or the end user of the system some explanation as to why the model predicted this initial label contradiction. And that is done by giving another example of where it would basically flip the label to something else. So these are some examples of the extracted latent features for some other example inputs. And I didn't want to add too many results here, but you can see that, most of these latent features are really high quality, interpretable, and actionable. So we don't have any data sets out there that have these kinds of features. So, if you use LLMs in this very systematic pipeline, you can extract a lot of interesting information that can be very useful for other kinds of downstream tasks. And these are some more examples here from this specific task, natural language inference. And we see that the counterfactuals that are generated are actually very high quality. And I didn't mention this before, but essentially these counterfactual explanations that we are looking for should be sort of minimally perturbed variations of the input. So we don't want an input that is completely, changed or different. So yeah, so, using our pipeline, you can get these really nice explanations, and it works really, really well for model explainability. All right, so in summary, in this work, we propose this pipeline that uses LLMs in a very systematic, off-the-shelf, simply prompting manner to facilitate these causal explainability. And we see at par or even better performance than the baselines, and we have no requirement for additional data or training. And the latent features, as I showed you, these are human understandable. And these basically provide evidence for the model decision. And I wanted to talk about some future work that can be done using, LLMs in these systematic pipelines. So other kinds of interpretability and robustifying models using these generated counterfactuals. So essentially, a lot of people ask me that how can I use LLMs in, model development and things like that in more systematic ways. And this is a great way of using these generated counterfactuals. So essentially, you generate a bunch of these counterfactual examples, and you can use this counterfactual data to train your models, right? So this is one of those use cases where you can use LLMs to generate really good quality synthetic data. And this last point is actually from another work that we did. You can uncover failure modes of your trained classifiers by using these counterfactuals. So you can essentially generate a lot of these test cases, generate a bunch of different test cases, adhering to certain different criteria, and you can use these to stress test your models. So lots of exciting directions here. And yeah, I have more results and more papers up on my website and the slides. All right, so I just wanted to show the community recognition that our lab's work has received. So the first paper that I talked about actually won an Outstanding Paper Award at a top NLP conference, and it has also been integrated into multiple benchmarks. So, it's up, it's open source, of course, free to use, and you can test it out on your own human and AI generated data. And let me know if it does not perform well. We have also seen really good performance of this framework on sort of other tasks as well that we didn't really test it on initially. So something like text attribution. So text attribution essentially is you have a piece of LLM generated text, and you're supposed to attribute it to which generator it came from. So the label set there is much bigger, and we didn't really optimize for that, but still we get the best and the most efficient performance there. All right, so that brings me to the end of this talk. These are I think this is the website. Yeah, this is the website QR code where you can get the slides, and I have a bunch of other slides from a tutorial I did on different types of attacks and defenses on LLMs. So feel free to check that out, and I can take any questions if you have. Yeah.
Are we moving toward trusted watermarks where my family, after they look at LinkedIn or look at any other social media or some newspaper or some publication, are we looking at generalized watermarks where they can start trusting? Yeah.
I think that is quite far into the future for now. Just because it's so difficult to implement in practice and deploy in practice. And also another issue with that is I don't think there is enough public education that is happening right now. So many people who are outside of our field are completely or significantly unaware of the technologies that exist and the harms that these technologies can bring. So, these two things need to happen hand in hand, education as well as making sure that these watermarks exist. Also, another point that I wanted to make is it's not really profitable for proprietary companies to have watermarks on in their models. Just because, you don't want, say I write an essay using ChatGPT, I don't really want it to get flagged by some AI detector. So why would OpenAI do that, right? So, yeah. Any other questions? Questions, comments, feedback? Yes. Yes. No, it's there. Should be public. Okay. Yeah. Exciting things. Yeah. That is a very interesting question. Okay. So at least we actually didn't test out with different temperatures or stuff, but from what I can tell, like we used a temperature of, I would say, zero point 0.4 for all of our generations. And of course, we ran it over, I think, 4 different seeds. And we didn't see too much of a difference. But I can understand where a temperature might have a significant impact on the generation. So I think this would work really well in lower temperature generations, but yeah, if you want to generate with a higher temperature, it might be interesting to see what happens. Yeah. Any other questions? All right, I'm gonna go back to this slide again. Thank you everyone.